Hi everyone, and welcome to this video today on the Laplace transform. The Laplace transform is useful in many different fields of science and engineering. My personal background is in electronics, so the viewpoint that I have of this tool is with that background in mind. Now I'm going to begin this video session by listing a number of areas in electronics where the Laplace transform is useful. The first one that I would like to mention is components. Electronic circuits are of course made up of components. Two of the most relevant components as far as this discussion is concerned are the inductor and capacitor. Now the relationship between the voltage across these components and the current through these components is in a form of a differential equation. So we will write that down to be clear what that relationship is. So for instance, if we take the capacitor, the current through the capacitor IC is equal to the value of the capacitor, which we will call C, times the change in voltage across the capacitor divided by the change in time, so dVc by dt. And of course this is a differential equation. Now for the inductor, the voltage across the inductor is related to the current by this equation here. So VL is equal to L, the inductance, times change in current divided by change in time. Now these differential equations are of course very simple because the components are not connected to anything, but of course a real circuit will have more than one component, and you can imagine that as the complexity of that circuit increases, then the mathematical expression that describes that circuit will also increase. And as the equations, the differential equations, increase in complexity, then it is difficult to solve the equations but also see what is going on. It is difficult to basically get an intuitive feeling of what the circuit is doing and how it's going to behave. Now, the second topic that I'm going to mention is really related to the first, which is the topic of filters. In electronics, we have two categories of filters: analog filters and digital filters. And analog filters are made up of inductors and capacitors, amongst other components, and therefore everything that I've said so far about point 1 equally applies to point 2. In addition, we have digital filters. In particular, I'm talking about IIR filters here, which have a direct correspondence to analog filters. And typically, people tend to use analog techniques to design a filter and then use the Z transform to map that analog filter characteristic into the digital domain. We will indeed talk about the Z domain in another video, as it's a very important subject. The third and final topic that I'm going to mention is, of course, control theory. Control theory is an area which is across disciplines, if you like. So often we need to control devices which are electromechanical. So it does involve the need to understand mechanical devices and express those mathematically. So we will basically make use of the Laplace transform to understand systems which are expressed in terms of differential equations. So what does the Laplace transform do for us? How does it make our life easy? Well, in a nutshell, what the Laplace transform will do is allow us to take an expression, a mathematical equation which is in terms of a differential equation or differential form, and transform that into an algebraic form. And then we can manipulate it in this algebraic form, and if need be, we can then transform it back into a differential form. Of course, the differential form here that we talk about is in the time domain. It doesn't have to be, could be some other domain, but we are talking about the time domain. And the algebraic form will be in the S domain, which we will get into as we go through this presentation. Okay, so next we are going to run through an example. The example that I have chosen is a mechanical one, and it involves the pendulum. We're going to look at the pendulum both in the normal direction, where the mass at the end of the string is hanging at the bottom, and also the reverse pendulum as well. And through this process, I'm hoping that we will learn a number of things which we can then apply in our daily working lives. So the first thing I want us to take away from this is to look at a problem, to think it through, and describe it in a mathematical form. And in this particular case, of course, we have a problem which it will be expressed in terms of a differential equation. Now, in this case, the differential equation is fairly simple, because we really want to understand the Laplace transform rather than get bogged down in lots of maths. But the technique, of course, applies to more complex systems. Once we have the differential equation, the second thing that we will pick up from this exercise is to take that expression and apply the Laplace transform to it and convert it into an algebraic form. And to do that, I will expand on the Laplace transform, write down the definition, and basically work through an example of how the Laplace transform is applied to a differential term, and then we will jump back to this example and actually apply it to the expression that we've derived. And then finally, once we have the system in an algebraic form, we want to visualize the character of that system, and we will do that for both the normal pendulum and also the inverted pendulum. Now, in this example, because it is simple, we can see what's going to happen in the two cases. Of course, the system could have been more complex and the behavior hidden and not so obvious, but hopefully the visualization aspect that we're going to pick up from this exercise will help us to appreciate the Laplace transform. Okay, so let's begin. Let's draw the system that we're going to consider. So let's say that this is the roof or the ceiling, and from this we are going to hang our pendulum. So here I'm showing the pendulum in motion. Imagine that this piece of string is very light, insignificant in terms of mass, and this is the vertical reference line and the point where the pendulum comes to rest, and there's an angle that's made between the vertical reference line and the position of the pendulum at any instance in time. Now, there are a number of forces acting on this pendulum. First of all, we have a mass at this end, and so there will be gravity, of course, which is simply mg. And I will have pushed this this mass to this position by applying some sort of an impulse, and that of course will be the torque applied in this direction. A torque is a force, of course. It is a force which causes a turning. So this is my torque. And what else do we have? Well, we will need to label the length of this string, because this mass has inertia. It is reluctant to stop, and if it's stationary, it is reluctant to start. So basically, once a body has reached a state, it is reluctant to change its state, and there is something called the moment of inertia, and the moment of inertia is given by this expression here: I is equal to ml squared. Now, if you have questions regarding the finer details, then send me an email or put a comment, and I will respond to it, hopefully, if I have time. But really, I don't want to get into too much detail regarding how these expressions are derived here, because that is not the main purpose of this exercise. So what else? We have gravity, we have torque applied to get the pendulum to begin to move. We have inertia, which is coming from the mass because it doesn't want to move. And of course we have friction as well. Now if we didn't have any friction, then this mass will continue to oscillate. But let's say that there is friction. So let's now include an expression for the friction. We're going to give this expression a symbol Fr, and we're going to say that the friction is equal to A times the angular velocity. A is basically a coefficient which tells us how much this mass will be affected by the friction. And of course the friction will depend on the medium that the pendulum is going to be swinging through. At this point I have all the expressions that I want to use to model this system. So let's write down the equation for this system. First of all, we have torque, and this is the turning force that we are applying to make the pendulum swing, and this is going to be opposed by the gravitational force on this mass, and the amount of the gravitational force which will oppose the turning force is equal to mgl sine phi. In addition, we'll have friction, and of course friction is always trying to slow a body down, so this is going to oppose the initial turning force that we apply to make the pendulum oscillate. So we include that, and then we also have the mass itself, and the mass is reluctant to move, and the expression for the reluctance, the moment of inertia, is now included. This is our complete system. These forces are now made equal to 0, but let's expand I so that we have ml squared, and then rearrange the equation so that it is in a more familiar form, a form which you'll find in many textbooks. Normally they don't include friction in textbooks, so this is an extra term being added here. And as you can see, this makes sense. If we take, for instance, the term representing friction, and you'll see that we have the coefficient, and then the coefficient is divided by the mass and the length of the string which ties the mass to the pivot point. And what you should notice is that if we increase the mass, then the value of this term is reduced, and if we increase the length of the string, then it is also reduced, which is basically saying the bigger the mass, the less impact the frictional forces of air or some liquid, if it's in a liquid, will have on the system, and it will basically oscillate for longer. And this makes intuitive sense. You can imagine if you had a pendulum and it was fairly heavy, then the frictional forces of air would not have much of an impact on that mass. Another term that we could look at is, of course, the turning force that we're applying. Now, if it was a heavy mass, then the amount of turning force that would be required would be greater. So let's imagine we apply a fixed turning force to a light mass. It begins to oscillate with certain maximum oscillation swing points, and then imagine that we apply the same amount of force, but we increase the mass significantly. And of course, intuitively you can see that the mass may not move as far because we really haven't applied enough of a force. And if the mass is large enough, of course, the reluctance of the mass to move may be so great that we may not be able to shift the mass at all. And I also want to mention this term here. This term here has sine in it, so it's sine phi, and this means that this whole expression is nonlinear, and so we need to do something about that to linearize the equation. And so we're going to assume that the angle angle phi is going to be much less than 1, which will allow us to rewrite this expression and replace sine phi with simply phi. Now we are going to get an equation. This is a differential equation. So now we're going to rearrange this equation, and the first term is going to be the angular acceleration, followed by the frictional term, which is dependent on the angular velocity. The third term will be with regards to the angular position of the pendulum at any point in time. And then we're going to make all this equal to the turning force that we apply. So the input into this system is the turning force that we apply, and the output, of course, is the angular position and the angular velocity and the angular acceleration. So this completes the description of this system, and the equation that we highlight here is a linear differential equation, which is of order 2, of course, because we have angular acceleration. So far we've talked about the Laplace transform and what it can do for us, but we haven't actually defined it or expressed it in a mathematical form. So let's do that. And what we're writing down here is the Laplace transform of a function ft. This is a function in time, and we're saying that to take this function from the time domain and transform it into the s domain, we must integrate it from 0 to plus infinity. This is, by the way, a single-sided Laplace transform because we are interested in causal systems, and therefore we don't consider functions which have a time value of less than 0. The function is multiplied by an exponential term, and the exponent in this exponential term is minus st. And s is a special variable which we'll explore as we go through these videos. And s is a complex value, so it has a real component as well as an imaginary component. And this whole expression looks very similar to the Fourier transform, with the exception that the exponent in the case of the Fourier transform did not have a real component. I just wanted to remind us all that we can write the exponential part in trig form. So for instance, if we had e to the power of minus j theta, we could write that down as cos theta minus j sine theta. I'm going to take the exponential term and expand it so that we can separate out the real and the imaginary components which form S. So we begin by writing e to the power of minus the real part sigma plus the imaginary in brackets, all multiplied by time, of course. And then this can be expanded into e to the minus sigma t times e to the minus j omega t. And of course, this can be simplified or manipulated further, and we can write down e to the power of minus j omega t over e to the power sigma t. Now the numerator, is in a form where we can expand it or convert it into trig form, which would then be cos omega t minus j sine omega t, and both these terms would be divided by e to the power of sigma t. And the reason why we do this is because we want to sketch the sinusoidal terms and show that because of the real component, we don't simply have a sinusoid which has a constant amplitude, but rather we have a sinusoid which is damped, which means that as time increases, the sinusoidal amplitude tends towards zero. So at infinity, the value of the sinusoid will be zero, assuming that sigma is positive. So let's sketch this. And we're going to simply sketch the first term. So let's begin by plotting a cosine waveform. And this is what we would have all the way to infinity if sigma was equal to 0. But of course we are going to also look at what happens when sigma is positive. In this case, we are going to sketch a guideline which will then allow us to trace a cosine which is being damped. So there are a number of important points on the time axis which we will mark to help us sketch the waveform out. Okay, so now let's begin to sketch the damped sinusoid. And there you have it, our damped sinusoid. So at this stage, what I would like to remind us all is that the real component in the complex variable s will force the sinusoid to tend towards 0 as time tends towards infinity if the real component is positive. If it's 0, then we will simply get a sinusoid which will oscillate without any change in amplitude. And if the real component was negative, then the sinusoid would actually increase in amplitude and it would continue to increase as time went towards infinity. These 3 points are important because they will help us later on to understand the character of a system. Before we move back to the pendulum system, let's just consider how we will use the Laplace transform to transform a differential equation from the time domain into the s domain. So here we're taking the Laplace transform of a differential equation f, or I should say df by dt. And to do this, we will use the definition that we must integrate the function df by dt from 0 to infinity, and of course we must multiply it by the exponential e to the minus st. We have two products, so we will carry out integration by parts, and we will remind ourselves of what that looks like. In this case, u will be equivalent to e to the power of minus st, and dv by dt is going to equal df by dt. So we are partway there. So if we integrate by parts, then the result of that integration will look like this. Actually, before we do that, we should put some limits on the integral. And now we can write down what the form of that integral looks like when we integrate. So we will have u times v evaluated over some limits minus the integral over the same limits of v by du by dt. Now we've defined what u is. It's e to the minus st, and therefore du by dt, which is simply the differential of that, will equal minus s e to the minus st. We've already said that dv by dt is equal to df by dt. And so it follows that the integral of dv by dt will simply be v, which is equal to f, and f of course is a function in time. So now that we have all the information that we need, we can go ahead and evaluate the first term. U is of course e to the minus st times f of t, and this will be evaluated over the limits, and of course our limits are infinity and 0. And then we look at the second term, which is an integral. The integral is from 0 to infinity of f of t times minus s e to the minus st. So we will take the minus out, and this minus that we already have becomes a plus. Now this is now looking at the first term, because we are going to evaluate it, we can see that if we substitute infinity for time and assume that the sigma is greater than 0, then at infinity, at time infinity, e to the minus st will equal 0, and so the multiplication with ft will simply be 0 as well. If we substitute 0 into our equation, then e to the minus 0t will simply be 1, and we will be left with the function f evaluated at time 0. Now let's look at the second term. This is an expression which you should recognize from the definition of the Laplace transform. And basically, if we take s out of this integral, and we can do that because of course s is not a function of time, then we are left with the Laplace transform of f of t times s. Okay, so we can say something now. We can say that if we take the Laplace transform of a differential term, then we end up with an answer which is basically the Laplace transform of the function ft times s along with initial conditions. So here the initial conditions are the value of f at time 0. If we assume that the initial conditions are 0, then we can say that the Laplace transform of a differential term is simply s times fs. This is an important result which we will make use of, and we will make use of it by simply looking at a differential equation and by inspection and transforming it into the S-domain. And of course this process can be repeated if we had a higher order differential term, and the number of times we would of course repeat this would depend on the order of the differential equation. Now we're not going to do this. We're here to basically learn the fundamentals, and for very complex systems we would of course use a computer. But before we begin to use computers, then we should have some sort of an understanding of what we are actually doing. So at this point I will simply write down what the expression would look like if we took the Laplace transform of an arbitrary large differential equation. So we end up with something which is s to the power of n minus fs, and this term is very important. I want you to remember this bit, and the remaining terms are all to do with initial conditions. And what I want you to remember is that if the initial conditions are set to 0, then the only term that will remain is the first one, which is s to the power of n times fs. So if we had a differential equation of order 3, then the answer would be s to the power of 3 times fs. The reason why I'm emphasizing this is of course because we will make use of this knowledge when we look at the pendulum system and we convert the differential equation from the time domain into the S domain by inspection. We've gone through the process of stating the definition of the Laplace transform, which tells us how we move from the time domain into the S domain. We've shown how the Laplace transform can be used to take a differential equation and transform it into the S domain, and also expressed how an nth order differential equation could also be taken from the time domain into the S domain. Now we're moving back and looking at the system, the pendulum system that we derived the differential equation for earlier on, and here is the second order differential equation. But to be honest, I would say that looking at this equation, if I hadn't actually gone through the process of deriving it myself, it would not have really spoken to me. So let's draw the pendulum system that we had earlier on again, and say a few words about that before we move on and study it further and transform this equation into the S domain. So we had a pendulum which consisted of a mass at the end of a string, and we had this vertical reference line, and the pendulum made an angle with reference to this vertical line. Now, what is the input to the system? Well, the input is the turning force that we apply to get this system oscillating. So the input will be T, and of course there are other inputs, but they are not inputs to the system from us. They are basically there whether we like it or not, such as gravity and such as friction, for instance, as well. And these other effects basically make up the character of this system. Of course there's an input, but there's also an output, and the output is basically the angle that we see. So this angle that's being made with reference to the vertical line is going to be the output of our system. The angle of course changes over time, and if we were to take the derivative, then we have a measure of the angular velocity, and of course if we take the second derivative, then we have a measure of the acceleration. So we have an input and an output, but in addition we have a set of parameters associated with this system. For instance, we have the coefficient of friction, which we have called simply A. We have the mass of the pendulum. We have the length of the string, and we of course have the acceleration due to gravity. And these parameters basically define the behavior or the character of our system. We are going to study this character, and we will study the characteristics of our system both in the time domain and also in the S domain. Now, the reason why we do this is because we are used to time, we live in time, and it is very easy for us to look at a waveform and make sense of it. The S domain, of course, is not where we live and think normally, and so it is more difficult to relate that to the time domain. So the approach that we will take here is to vary the parameters which control the characteristics, the character of our system, and then look at the response of the system to those changes in the time domain which we do understand, and also look at the changes in the S-plane due to those same parameter changes. And in this way, when we correlate the two domains with each other, we will gain an appreciation and develop intuition with regards to what happens in the time domain when we see changes in the S-plane or S domain. Once we have a good handle, a good feel, then we will not need to plot everything in the time domain any longer, and in fact we will be able to simply look at the S-plane, and based on what we see, we will be able to make good decisions as to how the system is behaving. So here we have the second order differential equation, and we're going to take each term in turn and we will transform it into the S domain using the knowledge that we gained a few slides ago. So the angular acceleration, which is given here in shorthand, can also be written in the conventional form, which is d phi, or of course we mustn't forget the 2's there because this is a second order differential equation. And when we transform this into the S domain, we will get S squared times U of S. Now U of S is simply a symbol that I've made up, and it represents the output. In a similar fashion, for the angular velocity, we can express that as d phi by dt, and when this is transformed into the S domain using the Laplace transform, we will get S times U of S. Now all of this, of course, we learned how to do earlier on. And then finally we have the angle phi, which is a function of time, and when this is transformed into the S domain, we will simply get we will simply get U of S. So we are now finished with the left hand side. Moving on to the right hand side, we have the turning force, the torque, which is a function of time, and when this is transformed into the S domain, we will simply get T of S. So notice that I haven't done anything with the parameters. Now the parameters are a constant, they are not a function of time, and so we don't have to worry about them. We can simply make use of them once we write out the full equation. And the other point to make is that the initial conditions are assumed to be 0, which will really simplify the set of equations that we generate. Now we are in a position where we can write out the full expression by taking these terms that we've generated. So u of s is common, so we're going to stick that outside. And inside the brackets we have s squared, and then we have a over ml squared times s, and finally we have plus g over l, close brackets. This completes the left hand side, and on the right hand side we simply have t of s over ml squared. So notice how the constant terms have simply appeared in the same positions as they did in the differential equation. Now we're going to manipulate this to generate the transfer function, and the transfer function is defined as the ratio of the output to the input, and it's typical to have two polynomials, one in the numerator and one in the denominator. In our case, we don't have a polynomial in the numerator, it's simply a scaling factor, but we have a second order polynomial in the denominator. So at this point we now have a transfer function in the S domain. Clearly this is the same system in algebraic form. And we will now study this transfer function in the S domain using the S-plane. And to do that, we will first need to determine the roots of the polynomial. Once we know the roots of the polynomial, then we will be able to plot those roots in the S-plane, and we will study how those roots change their position in the S-plane and correlate those changes with the time domain response of the system. Now that we have the equation, we're going to plot it using the S-plane, and the S-plane is complex. It has an imaginary component as well as a real component. We're going to begin by simplifying the equation and assuming that there is no friction, and as a result of this we end up with this equation which has a simplified denominator term. So we will set a, which is the term expressing the friction, to 0. The numerator is simply a scaling factor, and we will make that distinction by calling it scale. And the next job is to look at the denominator and find its roots. So we need to find the roots of the denominator to plot those roots on the S-plane. And here we have the roots. The roots are marked as two crosses, which are also known as poles. And the roots are placed at the square root of minus g over L and at minus the square root of minus g over L. G is the acceleration due to gravity, and L is the length of the string connecting the pivot point to the pendulum mass. Notice that the response of having these poles where they are is a sinusoidal response, and it has a constant amplitude which neither increases nor decreases. And this is the typical response, or the only response you will get from a system where the poles lie along the imaginary axis. And this makes sense because we are saying that there is no friction. If we were to push the pendulum and start oscillations, then those oscillations would of course continue until the end of time because there there is nothing to stop those oscillations. Now let's consider the case where we change the length of the string, we shorten it, and if we do that, then the pole positions will change. This is the origin point that you see, and we are moving away from the origin. This will increase the frequency, so shortening the length will increase the oscillations of our pendulum, and I'm sure you've played around with pendulums in real life, and you probably have seen that behavior. But notice that the amplitude has also changed. That's because the string length plays a part in the scaling of the amplitude of the sinusoid. So the string length has two impacts. It impacts the amplitude of the sinusoid as well as the frequency simultaneously. Now, if we had simply changed the mass on its own, then what we would find is that the amplitude of the response, the oscillations would change, but not the frequency. So the mass only changes the amplitude, but has no impact on the frequency, and that's because it appears in the scaling factor, but not in the denominator. Now let's consider the case where friction is no longer zero. And if friction is no longer zero, then we should replace the equation that we've expressed here by the one that we derived earlier on. So if we do that, you see the expression with a more complex denominator term, and of course A has a finite value, so we now have friction. The poles will no longer move along the imaginary axis, and they will actually move inwards along the imaginary axis as well as the real axis. And this is the result of keeping everything constant but simply changing the frictional factor. So as we increase the friction, and the poles move further in towards the negative real axis, and this has the impact of giving us a sinusoidal response, but this time it will decrease in amplitude. And this again makes sense from a physical perspective, because if you start oscillations by pushing a pendulum and we have friction, then of course the oscillations will eventually die away. So we can say that as time tends towards infinity, then the oscillations will actually stop. So you can see here that we have related what happens in a physical system consisting of a pendulum using the S-plane and the responses. So this system is inherently stable because the poles either move along the imaginary axis, never crossing the S-plane into the right-hand side, or they move towards the left if there is friction. And of course, in reality, there's always friction. So this represents a stable system. Next time, we're going to look at the reverse pendulum, which is inherently unstable. And we'll find that the poles now exist in the right-hand side of the S-plane. And so that's going to be covered on the next video on the Laplace transform. basically show us what we would expect to see in reality.